Okay, good morning. We'll start. Okay, so today is the third lecture. We'll talk about automatic differentiation. So the plan for today will be a very quick recap about differentiation, and then we'll dive into the main topic of today's lecture, which is how to basically differentiate computer programs. I will also talk to you about how it's actually implemented in some of the main deep learning frameworks. And then I will conclude today with a few examples beyond just training neural networks. Okay? So the lecture of today will be a bit more low level than the others. And what we will see today is not something that I suppose many of you, if any of you, will ever implement. But still, I think it's really important if you want to understand how these deep learning libraries do work, that you understand how they are themselves implemented below. Okay? And so this is a quote from Roger Gross, who is a professor, I think at CMU. And he says implementing backpropagation by hand is like programming in assembly language. It's something you study, but you will probably never do in practice later. But it's important for having a mental model of how everything works. And this is also true in deep learning. You will see that eventually, if you just want to train smallish neural networks, you can just use everything which is implemented for you in PyTorch or other libraries. But for example, as soon as you want, or you will have to scale up these models to something that, for example, that cannot fit in a GPU anymore, then you need to be a bit smarter, and to do that, you need to be able to, you need to understand what's going on below. Okay, so that's what we'll try to uncover today together. Okay, so why do I want to talk about automatic differentiation? Well, basically, as I've already told you last week and the week before, how do we fit and train this neural network is by using a gradient-based training algorithm, like gradient descent or stochastic gradient descent. But in order to run these algorithms, we need to have computed in the first place gradients. Okay? So this is what we'll see today, how to derive gradients automatically just from the description of a computer program or from the computer program running and then deriving the gradients automatically from this execution. We could have instead, and that's what you actually used to do in the past, derive gradients by hand, manually, okay? And that's something which is a bit tedious, but which we could do in principle. If you know how to differentiate composition of functions, then you can achieve that. But if you do that manually, then this is usually very error prone. So you will make small mistakes. And so that's an issue. And also it becomes very quickly impractical for complex models. So for the multi-layer perceptrons that we have seen last week, okay, we could do it manually once, and then that's it. But for all the other neural networks we'll see together, or when you will start yourself building your own architectures, then you will see that very quickly this model becomes complex. And yes, you could derive also the gradients by hand, but that would be quite laborious and error prone. Okay? Also, as soon as you would like, for example, to make changes to your architectures, you add a layer, you remove a layer, you add other connections, things like this, then you would need to basically rederive the gradients also. Okay? So we want to, because we are lazy, we want to avoid doing that manually, and instead design a procedure that automatically, from the execution of a program, would be able to differentiate it. Okay? All right. And basically, one of the main concepts we should remember is that a program can be defined as a composition of primitive operations, and provided that we know how to differentiate each one of these primitive operations, then we can just use the chain rule to compose the gradients of these bigger functions. Okay? And so this is actual Python code in JAX. JAX is one of the deep learning libraries. one of the main ones. And you see, you should be, I mean, even if you don't know JAX, I suppose many of you have used NumPy in the past, but even if you have not, this is quite readable. So in this case, for example, I define a predict function, which takes as input some parameters together with some input. Then I have a for loop where I iterate over the parameters. And then from the inside of this for loop, you can guess that I'm just computing a layer. Okay, so I do a dot product between a matrix and the input together with some offset that produce some value outputs, and then I pass this value through a tanh function, which is one possible nonlinear activation function. We've seen last week the ReLU or the sigmoid. We could have used that also. That produces some input, and then we iterate, and at the next iteration, we would use as input the output of that expression. Okay? So this is just a forward pass through an MLP. Okay, 4 lines of Python, 5. Then we would define a loss, and the loss would basically compare the quality of our predictions with respect to some targets. Okay, so that can be very easily defined as a function loss, which takes as input the parameters of neural networks, the input and the output. Then we predict the targets, given the parameters in the input using the previous function, and then we just compare these predictions against the targets in the sense, in this case, of the mean squared error. Okay? And since we want to minimize this loss, what we will need when we do stochastic gradient descent is the gradient of this loss function with respect to the parameters, so with respect to the params variable. Okay? And so how do we do that? We just call the grad function, which will produce as output another function which will correspond to the gradient of this function loss fun. Okay? So the lecture of today will be about how to implement this grad function. How is it possible actually that you can specify a computer program that takes as input another function and produce another function, which is the gradient. And what we'll see is that this is possible and actually quite easy. And the algorithm that we will see is actually an exact algorithm. We'll not even make an approximation of the gradients. We'll get the exact answer. Okay? We also see that we can compose these gradients themselves to compute, for example, higher order derivatives. So we can, for example, on this function, I could call similarly the grad function that would give me the first derivative of the tanh. Okay, but then that produces another function, in this case fp. And what I will also show you is that this function you can continue and differentiate it again by calling grad again on the function that is returned before itself. Do you have a guess about how this is possible? Because grad does not know in advance what the function will be passed as an argument. Yes?
Maybe by keeping the analytical expression of each operation.
Maybe, yeah. Okay. We'll see, it will be close to that. All right. So the family that we'll talk about today is the family of so-called automatic differentiation algorithms, which is a family of algorithms that you can use to evaluate the derivative of a function that are specified, or which is specified by a computer program. Okay? So there are other ways to compute gradients, other algorithms. One of them is the family of symbolic differentiation algorithms, in which you start with an expression, a symbolic expression, and then the goal of a symbolic differentiation algorithm is to give you back another expression, usually an expression which is human readable, okay, because you are interested in the symbolic expression itself rather than the values of the expression. There also exist other algorithms, numerical differentiation algorithms, like finite differences, which I suppose you have heard before. which you can also use for the same goal to evaluate the derivative of a function. But these numerical differentiation algorithms usually, and for most of them, are only approximate. Okay, they will not give you the exact answer. Okay, and so in our case, we'll not use that because we want the exact value of the gradient. All right, so let's start with a quick recap about calculus. So I suppose you all remember the concept of a derivative. So let's say we have a scalar function, f, that takes as input some real number and produces as output another real number. All right? Then, if you remember, we define the derivative of this function, which in my case I will usually denote in this way as the ratio of delta f over delta x. And I will call that the partial derivative of f with respect to x. Okay? But we could also denote this in this way with f prime of x. Okay? These are just notations. How do we define this notation is by this right-hand side, where we define the derivative as the limit of the ratio between the difference between f of x plus h and f of x, okay, over the offset h. Okay? And we take the limit of this ratio when the offset tends to 0. Okay? So what does that mean? It means that the derivative of a function represents its instantaneous rate of change. So if you have x on this axis and f of x on the y-axis, basically the derivative is the limit of the ratio. So when you compute the difference between f of x and f of x plus h, okay, you get this delta f, okay? Similarly, you can look at the difference between x and x plus h, which in this case is just h, okay? And then you compute the ratio between these two quantities, okay? The ratio between this segment and this segment, okay? All right? And now what you do is that you look at the value of this ratio as the size of this segment, of this interval, tends to 0, okay? As x plus h tends to be closer and closer to x, okay? And what you get is the derivative of the function, which is just the rate of change of the function, but instantaneously. Okay, with everyone? Okay. Okay. Then, from this definition of the derivative, you can introduce the definition of a gradient, where now we would have a function f, which takes not just one scalar as input, but a whole vector of n numbers. Okay? So the input now is a vector of n elements, and the output of the function f, however, remains just a scalar value, a real value. Okay? So now we can define similarly, or we can generalize our definition of a derivative by the concept of a gradient, which I denote with nabla f of x, which is a vector where you have as many rows as you have inputs, yes, and you have one column. Okay? And the element of these vectors are the partial derivative of the function with respect to each one of the n possible inputs. Okay? So it's just basically a big vector that gathers the partial derivatives of the function. Okay? Another way to see that is to say that the element j of this vector, okay, the element j of the gradient, is defined as the directional derivative of f in the direction of the canonical vector j. Okay? So it's the same definition, except that you multiply h with some vector. That's what we call the directional derivative. And when these vectors correspond to the vector of your canonical basis, then you recover the gradients. Okay? Okay, and finally, the last element that we need, and that's the object that we'll work together with today, is the Jacobian. So when we have now a function which is no longer just a scalar to a scalar or a vector to scalar, but a function mapping vectors to vectors, okay? So we go from vectors of size n to vectors of size m, okay? Then we can define the Jacobian as a matrix of size m by n. So we have as many columns as we have inputs, and as many rows as we have outputs. Okay? And each element of this matrix is simply the partial derivative of some output with respect to some input. Okay? And then we just basically iterate over all combinations of inputs and outputs. So we have, for this reason, m times n of them. Okay? So this is this form. We can also define this matrix in this way, where now you see the partial derivative of the function, so in this case the vector, with respect to each one of the inputs, or vice versa, using the gradients. Okay? Good. Questions? All right. Okay, so now that we have defined derivatives, gradients, and Jacobian, basically what we want to do is to define a computer program that will take some number of inputs, that will produce some number of outputs, and then we'll want to differentiate this program, meaning we'll want to evaluate the Jacobian of the program. Okay, that's the goal for today. Okay, we'll start easy and we'll first consider a simple chain composition, okay, where we'll say that we have some function f, again, starting from n inputs producing m outputs, and we decompose this function, okay, we rewrite it as a chain composition, okay, of t functions. Okay, so we say that the output of our function has been computed by first computing the output of some f1 function at the input that produce some intermediate quantity, which then we feed as input to a next function, f2, which produce another quantity, and so on and so forth. We repeat that t times for t distinct element, and finally, the final output has been computed from the penultimate output used as input to the last function ft to produce the final output of the function itself. Okay? And just in terms of notations, so I define this . Okay, and each one of these functions f, fk, is defined as a mapping from a vector of size nk minus 1, which is the size of the previous output, to another vector of size nk. Okay, I will use this nk over and over today. So, and we have that for k equals 1 to t. Okay? Okay, so in the diagram there, which corresponds to some graph of computation associated to this composition of functions, you also see the xt, okay, and I will basically define xk as fk evaluated at the previous value, xk minus 1. Okay, and all these xk are vectors of size nk. Okay, so far? So, if this is our function or composition of functions, the goal today will be to compute this. Okay, which is the Jacobian of the function. Okay, so xt is a vector, x1 is a vector. No, x1, x0 even. Okay, and we want to compute all the partial derivatives of all the outputs, so all the elements in xt with respect to all elements in the input vector, the very first input vector x0. Okay? How can we do that? The chain rule, okay? And in this case, what should we do? Yeah, and so on. So basically, to compute this Jacobian, we can use the chain rule, which in this case will tell us that the Jacobian is equal to the product of the partial derivative of xt with respect to its immediate argument, its immediate input, which in this case is xt minus 1, okay, times the Jacobian of xt minus 1 with respect to x0. Okay, and here you see that this is the recursive case. Okay, to compute this Jacobian itself, we can reapply this rule, but at xt minus 1 with respect to x0. Okay, so if we expand recursively this last factor, okay? This is what you have in the slide. We just apply the chain rule recursively on the Jacobians. Okay with everyone so far? Okay, now the question is, okay, so this is what I want to evaluate. I know that the expression associated to this Jacobian because of the chain rule can be this. Now the question is, how do we evaluate the value of this product of Jacobians? So how do you, if you were to implement this on a computer, what would you do? Okay, so what kind of object is this term? Is it a scalar? Is it a vector? Is it a matrix? Is it a tensor? Is it something else? Tell me. It's a matrix. What's the size of this matrix? Okay, so this is a matrix, and this is the shape of this matrix. All right? This term. Is it a scalar? Is it a vector? Is it tensor, a matrix, something else? What's your matrix? What's the shape of this matrix? Yes. Okay, and without any surprise, all the other terms will also be matrices. And the last one will be of shape n1 times n0. Okay, so basically what I'm just telling you is that if you want to evaluate this Jacobian, we could do so by rewriting it as a product of matrices. How do you evaluate the product of matrices? Sorry? The dot product with the lines, but yeah, I see what you mean, but where would you start? This one? And then what? I mean, I'm not asking trick question. Just tell me how would you basically implement that on a computer. So you would start from this term, yes, and then? Okay. So basically, you would say, first you compute this, okay, by multiplying these two matrices together, that gives you another matrix. And then you multiply this new matrix with, I suppose, the next term, and so on and so forth. Okay, but it's a product. So in principle, you could also do it in many other ways. Yeah. You could start from the last term. So we could have multiplied the two last together. That would have produced a new matrix, which then we would have multiplied with the one next to it, to its left, and so on and so forth, until we arrive to this last one, which is the first. Okay? Could we have done something different? No? Okay, I know that there are a few mathematicians in the room. Who are the mathematicians? Okay, could we do something different? Yeah, you can start from anywhere. Okay, if you have matrices, I don't know, A, B, C, and D, you could multiply these two, then with C, then with D, or C and D, then with B, then with A, or we could have multiply these two, then multiply these two, and then multiply the two of them together. Okay, we could enumerate many combinations actually. Okay, so in deep learning, usually we'll consider two, and the most natural one, the most obvious one, ways to compute this product of matrices. The first one is what we call the forward accumulation strategy, which corresponds to starting from the last term, okay, and then multiplying together with the one next to their left. Okay, so we start from the last two, then we multiply with this one, with this one, with this one, until we arrive to the first term. Okay, so for the forward accumulation, you take the product of matrices and you do the products backward. And for the reverse accumulation, you do with the strategy we've discussed first, which is to say you will multiply the first two matrices first, then together with the third, the fourth, the fifth, and so on, until you arrive to the last one. Okay? So to do the reverse accumulation, you just multiply the matrices in the forward direction of the expression of the product. Okay? And why do we say it's forward or reverse, even though I've just told you you go in the opposite direction of its name? Okay, because the forward and the reverse, they refer to the computations in the graph of computation. Okay? So the forward accumulation is called the forward because we first multiply the derivative corresponding to the first element in the graph of computation. Okay? So we would have for the graph of computation something like this. Okay? And we say we do it in the forward way because we first evaluate this part of the graph. Okay? We first compute the Jacobian of x1 with respect to x0, which happens to be the last term in the expression of the product. And then we multiply this, the Jacobian associated to this part of the graph of computation, by multiplying it with the Jacobian of x2 with respect to x1. Okay? And so you see that in this, when you follow the graph of computation, we are following it in the forward direction of the computation. Okay? Hence the name, even though when you look at the product of the Jacobians, it's as if we were doing it in reverse. Okay? And for the reverse accumulation, we would start from the end of the graph of computation, and at the end of the graph of computation, we would look at this term, which is the Jacobian of the output, xt, with respect to its immediate parent, xt minus 1. Okay? And then we will multiply the Jacobian that we would have computed for this part together with the Jacobian of xt minus 1 with respect to xt minus 2. Okay? And in this way, we would be following the graph of computation in the reverse direction, okay? Going from the outputs back to the inputs. Okay. So, which one should I pick? I have at least two ways to compute these products of matrices. Which one should I use? So if I compute my Jacobian using forward accumulation, I will get some answer, correct? Now, if I compute the same Jacobian using reverse accumulation, I will get also some answer. These two answers, are they the same or not? Can you raise your hand if they are the same? Okay, and if they are not? Okay, well, yeah, but I mean, assuming no numerical errors. Yeah, they should be the same. Okay? But is there an advantage of using one over the other strategy? Yes.
I guess it depends on the size of the input and the output of the chain composition.
Mm-hmm.
N0 is way bigger than the NNT, then the forward determination would be better.
What do you mean better? It will give the same answer.
Yeah, but it would be quickly because of the matrices multiplication and sizes.
Okay, so there is actually, so they will give the same answer, and you are correct in saying that. However, what may change is the number of computation required to compute these products. Okay, so the time complexity of these two strategies, they are not the same. Okay, and the time complexity of one or the other strategy will depend on the dimensions of all these matrices that appear in the product. Okay, and so the time complexity for the forward direction will be something like this, and the time complexity for the backward will be something like this. Okay, so let's derive these two things together. Okay. So this is what we want to compute, the Jacobian of xt with respect to x0. Okay? And using the chain rule, we have said that this was equal to this product of matrices. Okay. Now this is a matrix. What's the shape of this matrix? Yes. So we have some matrix AT of shape and T minus 1. Okay. Now this one will be another matrix, so of another shape, and the shape of this matrix AT minus 1 will be NT minus 2 columns and AT minus 1 rows. Okay, so this dimension and this dimension, they should match. Here we will have A2 with yet another shape, and 1 and 2, and finally maybe something like this, A1 and 1 and 0. Okay, and so we have two, we'll consider these two ways to multiply all these matrices together, either the forward or the reverse accumulation. Oops. Okay, so let me just draw this again because I will need this thing twice. Multiplied by this. Okay? Okay, so let's do the forward first. In the forward first, we consider the Jacobians associated to the first part of the graph of computation, which do appear at the end of this expression. Okay? So the very first step would be to multiply A1 with A2. Okay? And the result of this would be a new matrix of shape should be N1 here. After where? And 2 times N0, yes. And how many operations does it require to compute this product? At least. Yeah.
And 2 times
No. Okay, one of you said, yeah, this thing. Okay, so to compute, so we have in the output matrix, we have n2 times n0 elements. But to compute each of these n2 times n0 elements, we need to do this. Huh? Okay, so we need to iterate over the columns and over the rows. And how many do we have? We have n1 of them. Okay, so the cost associated to each of these n2 times n0 element is at least n1. Okay, so the cost of this operation of this thing here will be n2, n1, n0. Okay, that's the cost. Okay, next. So we have a product here also. And we'll have to multiply now this new matrix together with A3, which appears there, but I've not shown. Okay? What will be the shape of this resulting matrix? N3 times N0. And what's the cost associated to this product?
N3 times N2 times N0.
Yes. Okay? And so we can continue until we arrive to the last one. And now the cost associated to this last one would be nt times nt minus 1 times n0. Okay, and you can guess it from this sequence. Okay, and now the cost to compute this entire project is just the sum of all these costs in red. All right? And so the result is that we have to pay something proportional to n0, then k equal 1 up to t minus 1 of nk and nk plus 1. Okay? Ah, c'est toujours là. Okay, now let's do it in the backward or reversed direction. Okay, so we'll start from the same expression. Okay. Okay, so we can do the same. So in the backwards, we'll compute the product starting from the end of the graph of computation and computing the Jacobians associated to these parts, which appear first in this expression. So first we'll instantiate the Jacobian of the last element, so AT, so the Jacobian of xt with respect to xt minus 1, and then we will multiply that together with the Jacobian of xt minus 1 with respect to xt minus 2. Okay? So first we'll multiply these two matrices together. What will be the shape of this product? So we multiply a matrix of shape nt times nt minus 1 with another matrix of shape nt minus 1 times nt minus 2. Yeah. nt minus 2. Yeah. And what's the cost of computing this product? Well, we have nt times n minus 2 elements to compute, and the cost of computing each of them requires to enumerate all the columns and enumerate all the rows, and both of them are of size nt minus 1. Okay, so we just multiply all these numbers together, and we get nt times nt minus 1 times nt minus 2. Okay, next, we multiply this matrix with at minus 2. Sorry, it's minus 1. With at minus 2. So we have now this together with that. That gives us a matrix of shape yeah.
T times nt minus 3.
Yeah. And what's the cost of this? Yeah.
Nt times nt minus 2 times nt minus 3.
Exact. Okay, and then we can continue until we arrive there to compute the last product, which will come with a cost of nt, n1, n0. And again, now if we sum all these costs, that gives us the cost of computing this big product. And we have nt, which you see is common to all of these costs, times k equals 0, t minus 2, and k plus 1. Okay, so we have these two costs. You can see that they look very close to one another, but they are not really the same. And to make this a bit more obvious, let me rewrite this one. So I will just, maybe. So you see that in this sum, I'm going from 0 to t minus 2, and in this one, I'm going to 1, I'm starting at 1 and going to t minus 1. So they are not aligned with respect to the terms. Okay, but otherwise, it's about the same products inside. Okay, so I can just rewrite this by rewriting explicitly what is common to the two of them. And just to not make any mistake. So I would have first n0 so I'm writing the same, but I truncate this sum, I truncate off the last term. So I'm just going up to t minus 2. Okay, and then I have this last term that I'm putting aside. T minus 1 and t. And here we can do the same trick, but we remove the first term. Minus 2 and k. And then I'm putting it back. And t and 0 and 1. Okay? Now, why is it interesting to rewrite it in this way? If we say that this is negligible, and similarly for this term to the right, okay, we can just compare these two expressions. And they are exactly the same, except for the leading factor. If you do backward accumulation, the leading factor is nt, the dimension of the output. On the other hand, if you use forward accumulation, the leading factor is n0. Okay? So, assuming this last term it's negligible, basically you should prefer one or the other depending on whether you have more outputs than inputs or vice versa. If you have more outputs than inputs, then you should use this one because this sum will be smaller than this one. And on the other hand, if you have more inputs than outputs, you should favor this strategy because this term will be lower than n0. Okay? Okay. In deep learning, which one should we prefer? Forward or backward accumulation? On va planter ici. Which one? Yeah.
In deep learning, we can have billions of inputs, so I guess we should prefer the
So, the backward. Okay. Anyone else? So, those who would use forward in a typical deep learning scenario, like what we have seen last week. Would you go for the forward? Raise your hand. Would you go for the backward? Raise your hand. Okay. Why?
Because in most cases we will just have a few outputs for many inputs.
Mm-hmm. And in your case, how many outputs will we have typically?
One or two,
Why?
because it's either a classification or a reaction.
Wrong. Yeah.
For example, image classification, you will have a lot of inputs for pixels and the outputs will just be the class.
Wrong. You could have neural networks actually that predicts entire images. Like this is what we call, for example, a segmentation problem, where you start with an image and then you want to classify each pixel to say this is a person, this is the road, this is something else. So in this case, you would have the output of the neural network to be as large as the input. Okay, do you agree with that? And I would still recommend to go for the backward case in this scenario. Why?
We don't need the information about the inputs and outputs of the deep neural network, but the backward, the gradient descent, and the gradient descent is just to minimize the loss function. So the output is the loss function that we need to minimize.
Exactly, that's correct. That's the correct answer. So what do we differentiate? We differentiate the composition of the neural network together with the loss. And the typical output dimension of the loss is just one scalar, regardless of the architecture actually of the neural network. Okay, so for us typically, we'll have NT to be equal to 1. Regardless of doing classification, regression, segmentation, or anything more complicated, the losses usually will just be scalar functions. And for this reason, NT will be equal to 1. And so we'll be in this scenario of having many more inputs than outputs. Okay? On the other hand, I'm not saying this is also the optimal strategy. The optimal strategy would be so if we have a product of matrices A, B, C, D, E, would be to determine the optimal combination of these matrices to recover the lowest cost. Okay? But if you know how to do that efficiently, then you can stop doing what you are doing, and because this is an NP-hard. So except enumerating all possible combinations, we don't know a good algorithm for that. Okay, let's take a break, and we can resume in 10 minutes, more or less. Ok, on va reprendre. Okay, donc so far we have seen, we did a very quick recap about derivatives, gradients, Jacobian. The goal of today basically is to be able to derive an algorithm that will be able to compute the Jacobian of any computer program. Okay, and the very first instance of computer programs we have considered so far is just the case of chain compositions. okay, in which we express a program, a function, as a composition of smaller functions, where each takes as input the output of the previous one, produce some output, which is then itself sent to the to the next function in the chain. Okay? In this case, the Jacobian of the entire function with respect to the very first input can be expressed as a product of matrices, a product of Jacobians. We have seen that there are several ways then to compute this product of matrices. We've considered two of them, the forward accumulation and the reverse accumulation. They are equivalent in terms of the answer they will give you, fortunately. However, the time complexity associated to each of them, the time complexity of these two strategies, they are not the same. They can be derived as we did, and the main lesson for you is that when you are in a case where you have more inputs than outputs, or fewer outputs than inputs, then it's preferable to go for the reverse accumulation strategy. Okay? Okay, so now we'll consider something a bit more interesting, which is the case of a multi-layer perceptron, which is almost a chain composition, except that each function in the chain takes two inputs. It takes as input the output of the previous function together with parameters. Okay? So, all right. So we'll consider the case of an MLP. And to make things simple, we just consider one hidden layer MLP. So we go from vector to another vector with a linear projection. Then we'll do a nonlinear activation like a ReLU. We'll do another linear projection to produce one output. We'll just consider the regression case. And then we'll compare this single output to some target value in the sense, for example, of the squared error. Okay? So we'll have something like this. We have some vector x, which will map linearly to another vector. Okay? Just to make things explicit, then we'll have a nonlinear activation, sigma, which could be the ReLU, or the sigmoid, or something else, that will produce another vector of the same size as this one. Then we'll map this to a single element, a single value, which will be the output. Okay, and this value will be compared in the sense of some loss to some other input of that function, which will be the target in our case, and that will produce some final quantity. Okay, so I will call this one x0, this one x1, this one x2, x3, and x4. Okay? And what I'm saying is that we can rewrite this in this form, okay, for some specific choices of f and theta. Okay? So let's do that. All right. So we'll have x0 entering f1 together with some parameters theta 1 that produce x1, then f2, theta 2, f3, x3, okay, and how is this equivalent to that? Well, it's equivalent if I say that x0 is my input x, okay, and it's a vector of shape n0. Then I say that x1, this guy, is the output of f1 evaluated at x0 and theta 1. Okay? Which, in the case of an MLP, okay, is this first linear projection. So we have f1, x0, and then in a linear layer, the parameters theta are given in a matrix. Let's call it W1. And the output is just the product of that matrix with the input vector x0. Okay, then we have x2. So x2, oh, sorry, it should be there. X2 is f2 evaluated at x1 and theta 2. Okay. X2 is the output produced by the sigmoid or the ReLU evaluated at x1. Does not take parameters. Okay, so this second argument here is empty. And it's just then given by the nonlinear activation sigma at x2, at x1. Sorry. Whoop. X3 now. It's f3 evaluated at it's 1 here at x2, and x3 is this one, so it's the result of another linear projection where we go from a vector of size n2 to just a scalar. Okay? So we'll call this W3. Okay, and we'll have W3 times x2. And this quantity will correspond to the prediction y hat of our MLP. So this one will be y hat or x3. The target will be y, this one. Okay, and now we'll have the last part of this graph of computation, which will correspond to the loss evaluated at our prediction y hat and the target y. Okay? So we have x4, f of x3 and y. Okay, and I will define this as 1/2 of x3 or y hat minus y squared. Okay, so now that we have this, what do we want to compute? Yes.
It's a question.
Yes.
At what corresponds the y above the loss function?
It's the target value. So in your training set, you have pairs of inputs and outputs. The inputs are the x, the outputs are the y. Okay. And now what this loss, so for example, in this case, this L function, this L is simply the squared error. Okay. Where you compare your prediction, x3 or y hat, against the ground truth value y that you know and have access to in your training set. Okay, but these are just basically constant in a sense of this graph of computation. Okay, but conceptually it's just also just a variable that you feed as input to this L function. Okay. All right. Okay. So if we want to train this neural network, what do we do? What have we seen last week? Yes.
Compute the gradient with respect to the weight parameters to perform the gradient descent.
Exactly. So we'll run gradient descent or stochastic gradient descent or a variation of that. But to run this algorithm, we'll need the gradients of the loss with respect to each and every parameter of that architecture. Okay, and in this case, the parameters that we have, well, we have this one, theta 1, which corresponds to this matrix. Okay, so W1, which is, by the way, a matrix of size n1 times n0. Do we have a parameter for f2? No, we do not. Okay, so this we can remove. Then we have f3, which is given here, which is a linear projection, where we linearly project x2 with some w3. What's the shape of w3? Well, since this guy is a scalar, okay, this is actually not a matrix, it's a degenerate matrix, because it has only one row, and then it has as many columns as we have element here, so which is n2. Okay. So this one now is just a real value. This one is not a parameter, okay, because it's fixed by the training set. Okay, but this will be y, and that will be a scalar. Okay, so we have two free parameters, W1 and W3. And so if we want to optimize the architecture, we need to optimize its parameters. And to do that, we require the derivative of the loss, the gradient of the loss with respect to W1 and W3. Okay, so let's start with this one, theta 3. So what we want is the Jacobian of x4 with respect to theta 3. Okay? How can I expand or rewrite this Jacobian? Yeah.
The Jacobian of x4 with respect to x3
Yes. So we just use the chain rule and rewrite it as this product of two Jacobians with respect to theta 3. Okay? Okay, now let's be a bit more concrete. What is this term?
Matrix.
It's a matrix. What's the shape of this matrix?
N4 times N3.
Okay. What is N4?
1,
1. And what is N3?
1, 2. It's a scalar.
Okay. So in this case, it's a 1-by-1 matrix, which indeed is just a scalar. And what's the expression of this single element? Now you just, so how do we do that? We need to differentiate x4 with respect to x3. Right? Everything is scalar. That's easy. So we need to differentiate this expression with respect to x3. What do we get? What do we get?
X3 minus the target.
Yes. Okay, then we have the second term now, this, which is also a matrix. What's the shape of this matrix? So you have always as many columns as you have inputs and as many rows as you have outputs. So x3 is the number of outputs. The dimension of x3 corresponds to the number of outputs. x3, we have said it has a size of 1. So it's a matrix of size 1 times the number of inputs, the number of elements in theta 3, and the number of elements in theta 3, okay, is N2. Okay, so I will write it as in this way. It's the dimension of theta 3, okay, which in this case would amount to this. Okay, so this can be a very long vector. Okay, it will be as long as the width of our hidden layer. Okay, and what do we have inside? Okay, so we have x3, which is w3 times x2. Okay, I've told you that w3, where was it? It's a very long vector. Where you have one row and two columns. And then we multiply this with x2, which has one column and two rows. Okay, so now we need, what do we need there? Yeah? Transpose of x2. Yeah, and how do you arrive to that?
The Jacobian of x3 with respect to theta 3, the partial derivative of each element of w3 x2,
Mm-hmm.
and each element is, so it's w31 x21, w32 x32,
Mm-hmm.
and if we do the partial derivative with respect to x21, for example,
Mm-hmm.
it's with the
Yeah. Okay, so if you have not all followed, we have elements there, okay, and at some position j, what do we have? We have the partial derivative of the output with respect to the parameter at position j, okay, which in this case is the element in this matrix, how do I call it? W3, yes. And I take the element at the first row, well, I only have one anyway, and position j. Okay, so this W1J3 is just one variable. Okay, so this can be helpful because now if you think in this way, when you will multiply this vector by another vector, you will do this. Okay, so you will iterate over the columns, the j, okay, and you will do W3 I j times x2 j. Okay? And now in this way, when I'm asking you if you differentiate this expression with respect to one of these variables, okay, the only thing, so almost everything disappears except the associated value for j in x. Okay, so we have that this is equal to x2j. Okay, so all of that to say that this entire vector here will be x2 transposed, as you said. Or maybe I will start there. Okay, so we know the first gradient for updating these parameters. But we still need the gradients for updating these ones. But we can do the same. What we'll have to compute is the Jacobian of the output with respect now to these other parameters, θ1. Okay, we can apply the chain rule of differentiation, and that gives us the Jacobian of x4 with respect to x3 times the Jacobian of x3 with respect to x2 times the Jacobian of x2 with respect to x1, and finally the Jacobian of x1 with respect to θ1. Okay, so let's do the same. So this guy we know, it's the same as previously. So it's again just a scalar inside a 1-by-1 matrix where we have x3 minus y. What about this one, this matrix? Is it the same as this one? No, okay? Because now we are differentiating with respect to x2 and not with respect to θ3. Okay? But it's still computed in the same way, and so we'll still be differentiating this expression, but now with respect to x2. Okay? So what will be left are the W values. So we'll have a vector, again, of the same shape as before. I mean, of the shape of x2, so that's n2. where at each position j will have the derivative of x3 with respect to x2j, okay, which is w3, 1j. Okay, so this Jacobian is the weight matrix itself. Okay, next we have this term, the Jacobian of x2 with respect to x1. So x2 is the result of, you start from x1, you go through a nonlinear activation function, and that produces x2. Let's consider the case to make things simple that we define this as ReLU of x1. Do you remember how we have defined the ReLU activation function? Yeah.
The max between 0 and the input.
Okay. So the ReLU, if this is its input, we have something like this. Okay, so if the input is negative, we return 0. If it's positive, we return the input itself. Okay, so what's this matrix? So it's a matrix where I've told you you have as many columns as you have inputs, as many columns as you have inputs. So in this case, we have n1 inputs, and you have as many rows as you have outputs, so n2. Okay, but what do we have inside?
It's x if it is positive, or 0 if it's negative.
Nope. It's 0 when it's negative, that's correct, but it's not x when it's positive. It's 1. Who said that? Yeah, it's 1. Okay? So the derivative of this linear, of this line, okay, is given by the slope, okay, which is 1. So we have a matrix with 0 everywhere, and on the diagonal we'll have ones or maybe zeros depending on the value of x at the corresponding element. Okay? And we'll have that this element j will be equal to 1 if the element j in the input vector, which is x1, is positive. Okay? Okay, let me write this here. Okay, and finally, we have this guy. Which is a matrix. What's the size of this matrix? So how many rows do we have? Oh. We have as many rows as we have inputs. No, as we have outputs, which is n1. and how many columns? As many as you have inputs. Okay? So in this case, we have as many as the size of theta 1. Okay? But I've told you that theta 1 is this matrix W1 of shape n1 times m0. Okay? Okay, so I will replace, so to make things more or less simple here, I will do as if I was flattening my matrix into a big vector, okay, and the size, and so this quantity here would be the product of these two dimensions, n1 times n0. Okay? We can actually re-express this whole algorithm or this whole thing using tensors, but I will spare you the notations. So just assume we flatten everything. Okay? In this case, it's as if we had transformed this matrix into a long vector. Okay? And this long vector include n1 times n0 elements. Okay, so we have a long matrix here. And what do we have inside? Yeah.
Weights of W1.
Sorry, we have x?
No, weights of W1. The values of W1.
No. No. Okay, so let's do it here. Oh, I will do it like this. So we have x1 being equal to W1 times x0. Okay? Which when I write in this way, I have this matrix W1 times this vector x0. Okay? So this is n1, n0, n0, 1. Okay? Which means to compute the output j, okay, the element j in this vector, okay, what do? Well, I select this row, this single column, okay, and I compute the corresponding products, I sum. So in this case, I iterate. Now let's call it, sorry, I. Otherwise, it will be messy. I iterate over j. So I am at row I, then I iterate over the columns j of W1, and then I select the element j in x0. Okay. So now when I differentiate with respect to x with respect to this, with respect to the W, what I have left is the x0j. Okay? And so that means so what you should understand is that so we have as many columns as we have elements in the entire W. okay? But among all these columns, okay, we only select the elements that happen there in this expression, which are those at row I. Okay, but since we have concatenated everything, it means that this W flattened, okay, it's made of blocks like this, each of size and 0. Okay? And now, if I want to compute the derivative of x, sorry, where am I? Of x1, this one, with respect to this, I know that it should be non-zero only at the values that happen there in this expression. Okay? So that means this thing will be divided into a big block matrix like this. And if I look at, for example, this row, the row I, which corresponds to the I output of my function, okay, I know that I will have 0 everywhere, but at the values associated to these elements, okay, in this expression. Okay? And so now when you differentiate this, the only thing you are left with when you differentiate with respect to the W's are the x zeros. Okay? So here what you have is x0. Okay? And so if you do that for all blocks, you have a block diagonal matrix where each block on the diagonal is the x0 vector itself. Otherwise, it's 0 everywhere else. Okay, so now we have we have an expression for everything. We can compute all these products, and we have the two Jacobians that we require to do stochastic gradient descent. Questions on this? I mean, it's a bit laborious, but if you just stay a bit in front of these expressions, they will eventually make sense if they don't make sense yet. It's just differentiation and then composing these primitives together. Okay, so now we can differentiate the parameters of the MLP. And now we are ready to generalize that to arbitrary computer programs, where I will basically define a computer program as a function f that takes as input s input variables, each of them being vectors, possibly. And then I will say that the computer program f, taking these s inputs, well, it's implemented by producing a certain number of intermediate values, xs plus 1, xs plus 2, up to xt. Okay? So t will be the total number of variables, okay, all the input variables together with all the intermediate variables. Okay? And I will say that this very last variable, so xt, will actually correspond to the output of my computer program. Okay? Similarly, I will say that each of these intermediate variable or each of these variable xk is a vector of size nk. Okay. And now that I've expressed things in this way, when I say that I want to differentiate my computer program, it means that I will want to evaluate all the Jacobians of the function output with respect to each of the S input vectors. Okay? So the goal of automatic differentiation will be to obtain the value of all these S Jacobians. Okay, but if I define this in this way, then it becomes obvious that my computer program or the execution of my algorithm will correspond to a succession, to a series of instructions, okay, each being of the form. We start from some subset of intermediate variables that we've already computed or that are given directly as input to the program, okay. We run some instruction fk, some function, and that produces a new variable xk. Okay, and I'm repeating this mechanism for different functions fk. Okay, up to the last ft, which will produce the xt variable, which is the output of the program. Okay, what is important in this formalism is that each of those functions fk, they will depend on other variables, but only those that have been computed before. Meaning that they will only, fk can only depend on x1, x2, and so forth, up to xk minus 1, but will not be allowed to depend, for example, on xk plus 1, because it has not been computed yet. Yes?
So it means that this formula is not valid for recurrent
No, because if you take a recursive function, you can always rewrite it iteratively with a for loop, which is a series of instructions. Okay, so the diagram you should have in mind now is this one. We have a certain number S of inputs, they are vectors. Then we use these vectors to compute some temporary intermediate variables, okay, because we need them eventually to compute the final output xt. Okay, and now each node in this diagram corresponds to one of these variables, and we have a connection between two nodes if to compute, for example, xk, the function fk requires directly these other variables. So for example, here we would have that we have a connection from S to S plus 1 because to compute S plus 1, we have expressed that as a function which depends directly on xs. And also in this case on x2 and x1. Okay? So we put connections between nodes if they are immediately connected in the sequence of instructions. Okay? And now that we have this as a graph, the execution itself of the program will correspond to a forward path through this graph. Okay? Going from inputs through intermediate variables to the output. Okay? All right. So we'll see two ways to compute the Jacobian. The first one is called the forward mode of automatic differentiation, and the second one will be the backward mode of automatic differentiation. Okay, in the forward mode, what do? We'll be computing this Jacobian starting from the inputs, starting from the input parts of the graph of computation, and then growing and moving to the output, exactly as we did before with the forward accumulation. Okay? So we are computing this Jacobian of xk with respect to x1, one of the inputs, okay? And we'll do so by just doing that within a loop that goes from k first at s plus 1, then s plus 2, up to k equal t, the output. Okay? To run this algorithm, we need first to initialize the Jacobians of all the input nodes. Okay, so we'll have that the Jacobian of the variable, for example, x1 with respect to itself will be given by the identity matrix of size n1. Then we'll have that the Jacobian of all the other inputs with respect to x1 will be 0, okay? Because we assume that they are not connected, they are independent, so their Jacobians are all set to 0 matrices. Okay? And now the algorithm goes like this. We have this loop in which, for which at each iteration we obtain the next Jacobian of xk with respect to x1. So let's say we've run already the algorithm from x1 to all these intermediate values. Okay? Then we'll say that the Jacobian of xk with respect to x1, okay, it's what? It's the sum over all the parents of xk. So that means with respect to all the immediate inputs of xk. And for each of them, you compute the Jacobian of xk with respect to these parents, okay, xl. And then you multiply this with the Jacobian of xl, the parents, with respect to the inputs. Okay? So we are just applying the chain rule again. Okay? And then we grow, we move from the k close to the inputs up to the output. Okay? Okay. In terms of notations, you see these brackets. Okay, so everything, all these two terms, they are Jacobian, so they are matrices. Okay, but I use the brackets to denote the on-the-fly computation of the Jacobian that is locally associated to the primitive of xk. Okay, while this one will already have been computed from the previous iterations. Okay, this Jacobian of xl with respect to x1 are matrices that correspond to this part, but if we iterate going from the left to the right, we have already computed these Jacobians. So we store them because we know we'll reuse them for the computation of the next Jacobians. Okay? And so these ones, they are already known from before, and the only thing really that we need to compute is this one. Okay? And once we know it, we multiply it with the previous ones, we sum everything, and we get a new Jacobian. Okay, so let's consider one example. Okay. Okay, so let's consider another function than the MLP, which I define as x2. So we have two inputs, x1, x2, and I say that the output is x2 times the logarithm of x1, okay, whatever, plus the square root of x2 times log x1. Okay? Just for the sake of the illustration, I will assume that that both x1 and x2 are scalars. Okay, so just to make things much simpler. But if I rewrite this expression as a program and specifically as a graph of computation, I would have a first node for x1, a second node for x2, then possibly some intermediate variables up to a final node which would correspond to the output. So this whole expression. Okay? So if we were to implement this on a computer through a sequence of primitive operations, how would you do that? Yeah.
First, log of x1
multiplied by x2, it's log of f1, it's a new node. Multiplied by x2, it's a new node.
Yeah, so let's slowly. So let's say we compute the log of x1 and we store that in x3. Then what?
Then a new node is 4 that is depends on x2 and x3.
Yeah, by the way, I have this. Then x4, which is what? Which is the product of x2 and x3, I suppose. Okay. x2, x3. Then what?
And since it's the same term on the right,
Yeah, so you see that this term and the inside of the square root are the same, so we can just compute them once. That's x4. Yeah.
so x5 depends on x4.
So we define x5, and we say that it's equal to the square root of x4. And finally, yeah.
6, that is x4 plus x5.
So it's x4 plus x5. Okay, meaning it depends on x5 and not this one. Okay. And now what we want to do is to differentiate the output of this program with respect to its two inputs, x1 and x2. So let's first do this one. What's the first step of the algorithm? We need to initialize the Jacobians for the input nodes. So we have this step. So first we have okay, and the Jacobian of x2 with respect to x1 is 0. Then we have to run this for loop, going from k equal s plus 1, so 3, up to t equal to 6. Okay, so we have 4 iterations to do. Yeah. And so at every step, we compute the Jacobian of xk with respect to x1. So at the first iteration, k is equal to 3. So we compute the Jacobian of x3 with respect to x1. Okay, and then we just apply mechanically this expression. We sum over the parents of k. The parents of 3 is x2, is x1. Okay, x3 is connected to x1 only. So this sum is made of one term. And we have x3 with respect to x1 times the parent with respect to x1. Okay. What is this term? It's the Jacobian of x3 with respect to x1. Okay, everything is scalar, so it's just the derivative of log of x with respect to x. Which is 1 over x. Yeah. And this derivative of x1 with respect to x1, well, I've told you the only thing we would compute at each iteration is what's inside the bracket. So this thing we should have from before. And indeed, we have it there because of the initialization. So we can just replace this thing by this, which is 1. Okay, so we get 1 over x1. Do you want to do a last break? I think I will take 30 more minutes or so until the end. No? Okay. So where were we? Okay, so what do I have to do next? Yeah. And what? X1, sorry. Okay, so what is this guy? Where is my graph? Okay. So we have to compute the Jacobian of x4 with respect to x1. Okay, and if you apply this, the chain rule, we have to sum over the parents of x4, so x3 and x2, and for each, we compute the Jacobian of x4 with respect to these parents times the Jacobian of the parents with respect to x1. Okay, so in this case, we have two parents, as I said. X3 plus Jacobian with respect to the other parent x2 x1. Okay, what is this Jacobian? So the derivative of x4 with respect to x3. So the derivative of x2 times x3 with respect to x3. x2. Times this, we should have it there, so it's 1 over x1 plus the derivative of x4 with respect to x2. So the derivative of x2 with respect to times x3 with respect to x2. That's x3. Times the derivative of x2 with respect to x1. Where is it? It's 0, this one. Okay, so this is equal to x2 over x1. Next. Well, next, k equal to 5, so derivative of x5 with respect to x1. What are the parents of x5? We have only x4. And we do derivative of x5 with respect to x4 times this. Derivative of x5 with respect to x4. So the derivative of the square root. So 1 over 2 of 1 over x4 times this thing, which we should know from before, and indeed, that's what we have computed there. So we know that this quantity is equal to this one. And finally, x6 with respect to x1. What are the parents of x6? It's 4 and 5. So we have two terms in this sum, two parents. And 5, yes. x5, x1. Okay, derivative of x6 with respect to x4. So if x6 is just the sum of x4 and x5, if you differentiate with respect to x4, you get 1. 1. Who said x5? I know it's a long time ago, but you see eventually that's useful. So 1. Then this thing we should have from before. It's there. x2 over x1 plus the derivative of x6 with respect to x5. So now it's your time to shine. No, it's still 1. If you differentiate this expression with respect to x5, you get 1. No worries, everything will be implemented for you. And this thing, which is this expression. Okay, so we have that. Okay? Okay, so we've computed the Jacobian of the program with respect to the first input, but we have two inputs. So we have to do that again. Okay, so I will not do it, but we should then run the same kind of loop to compute this thing. And do it yourself. It's a good exercise. Okay, so that's for the forward mode of automatic differentiation. What you see from what I've just said is that if we have to repeat this whole procedure as many times as we have input vectors. So we have to repeat that s time, and if we have many inputs, which will be the case for us because our number of inputs will be the parameters, the number of parameters. So we don't want to repeat this thing millions of times because we have millions of parameters in our neural network. However, there is still an advantage to this, is that the cost in terms of memory required is quite low because we only need to store the temporary variables and we can free them as soon as their child nodes have all been computed. So if you have a very big neural network, so big that we can't store all the intermediate values, that might be something useful. Okay, because we'll be able to compute these gradients on the fly as we compute the forward values, as we compute the intermediate values, without blowing up in memory. Okay, next, it's the equivalent of the reverse accumulation, which we call reverse mode autodiff. Okay, it's the same objective. We want to compute the Jacobian of the output with respect to each one of the inputs, but we'll do so by traversing the graph in reverse from the outputs to the inputs, instead of going from the inputs to the outputs. Okay, so we'll compute a sequence of Jacobians, and the Jacobians we'll compute will not be the same as before. Okay, what we'll compute is Jacobian of xt, the output, with respect to the intermediate variables and the inputs, and we'll do so starting from t, instead of starting from s plus 1, down to 1. Okay, instead of up to t in the forward mode. And so what do? First, we initialize the Jacobian of the output node, okay? Before we were initializing the Jacobians of the input nodes. Now it's the output node. So the Jacobian of xt with respect to itself, it's the identity, okay? So in this case, it's a matrix if we have empty outputs. And then, what do? We run this for loop where we go from k equal to t minus 1 up to 1, and at each iteration, okay, so we are traversing now the graph starting from the outputs back to the inputs, okay, from the right to the left. And then at each iteration, we will be computing the Jacobian of xt, with respect to xk, okay, and we'll use the chain rule to say that actually the Jacobian of xt with respect to xk is the sum over all the child nodes of xk, okay, this one, xm, xm prime, and so on, of the Jacobian of xt with respect to these child nodes, these child variables, times the Jacobian of xm with respect to xk itself. Okay, so again, this is the chain rule, but now for this other part of the graph of computation. And again, there are things we'll have computed from before. So the Jacobians of xt with respect to everything after xk will have been computed before in the previous iterations. So all these ones will be known. And the only thing we'll have to compute are all these Jacobians that are associated to each one of these primitives with respect to their, in this case, same parent xk. Okay, let's do it. You will see it's not complicated. Okay, so this was for the forward. And now we'll do the backward. And we'll compute the same Jacobians, so this one, over that same graph. Okay, but using now this second algorithm instead. Okay, so what do we have to do at initialization? We have to initialize the Jacobian of the output nodes. In this case, we have one output node, so we have x, the Jacobian of x6 with respect to itself. This is equal to 1. Next, we have this for loop going in reverse from t minus 1 back to 1. So at the very first iteration, what will we be computing? Yes. Okay, so we iterate over this index, okay, at the denominator. Okay, and what do we have to do? So we have to consider all the child nodes of x5. So the child nodes of x5, we have one, which is x6. Okay, so we have a loop, we have a sum over one element. And we have x6 over that child node x6 times x6 over x5. Okay. As for forward AD, in backward AD, there are terms we know from before. This one, okay, which indeed we know from the initialization. And now we need to compute the derivative of x6 with respect to x5. Yes. Okay, so 1 times 1, 1. Next, what do we have to compute? Derivative of what with respect to what? Yes. Okay, so x4. What are the child nodes of x4? We have 5 and 6. So we have two terms now in this sum. So for the first one, we would have x6 times x4, or no, we have 5 and 6, yes. x5 times the derivative of 5 with respect to 4. Plus derivative of 6 with respect to 6, yes, times derivative of 6 with respect to k, so 4. Okay, derivative, this one we know from the previous iteration, it's 1. Then we have to differentiate x5 with respect to x4. So we have to differentiate again the square root. That's 1 over 2 over the square root of 4, x4. Plus this one, which we should know, it's 1, times the derivative of x6 with respect to x4. Thank you. So that's 1 times 1, 1. Next, x6 with respect to x3. So what are the child nodes of x3? We have 1, it's 4. So one term, which will be about x6 x4 times x4 x3, yes. Derivative of 6 with respect to 4 is what we've computed just there. So it's 1 over 2 square root x4 plus 1 times the derivative of x4 with respect to x3. So the derivative of this with respect to x3, x2. do it there. So we were there. 2 more. Jacobian of x6 with respect to x2. Oh, zut. So, the child nodes of 2, we have 1, which is 4. Okay, so 1 term. So, x6, x4 times x4 over x2. Derivative of 6 with respect to 4 is no, it's the wrong one. It's this one. So 1 over 2 x4 plus 1 times the derivative of 4 with respect to 2. This one, so it's x3. Is it correct? Okay. And finally this one. So for 1 we have only 1 child node, x3. X6 with respect to the child node of 1, 3 times the derivative of 3 with respect to 1. Uh, 6 with respect to 3, it's this one. Plus 1 times x2. And the derivative of 3 with respect to 1. So it's the log of x, so 1 over x1. Sorry, 1. Okay, and I've told you these 2 algorithms should give you the same answer. Otherwise, I made a mistake. But so, using forward AD, we said that we arrived to the fact that the Jacobian of 6 with respect to 1 was being equal to the sum of x2 over x1 and of 1 over 2 over square root of x4 times x2, x1. Okay, so this is, I can factorize out this ratio. Have this, and it's the same as that. Okay, and what is also nice about this algorithm is even though we have done only one run of the algorithm, if you paid attention, we've also computed that second Jacobian for the second output, for the second input, which is the thing I told you to do by repeating the algorithm once again, the forward algorithm. Okay? Here in one go, we get the Jacobians for all the inputs, which is nice. Okay, so the advantage, as I just said, is that you get all the Jacobians at once. However, there is a price to pay. Of course, it does not come for free. Is that you have to store all the intermediate variables. You cannot free them as you go, as we could do for the forward model autodiff. Okay, so meaning that the cost can be quite substantial if you have a very large graph of computation. Questions on this? Good. All right. So now I want to just give you a few words about how it's actually implemented, even though we'll not study the actual implementation, but if you want, you can just check the source code associated to the main deep learning libraries. So in this course, we'll use PyTorch. But there are others. TensorFlow is one another, and JAX is also another. But they have differences, but they work more or less all the same when it comes to implementing automatic differentiation. If we take, for example, the case of JAX, basically in JAX, there is a language which you don't see, but to which everything you write in Python is translated. Okay, it allows you to define high-level functions, and then the library will basically unpack these functions into this lower-level language made of primitives. And then what will happen below is that each one of these primitives will know how to differentiate itself with respect to its immediate parents, with meaning each of them will know how to compute this kind of bracket Jacobian. And if everything you write is a composition of this primitive which know how to differentiate themselves, provided that you have access to the graph of computation, you can just run forward or reverse mode autodiff in the direction that you want on that graph, and then you get access to the Jacobians. Okay? So it's exactly like that that it's implemented. So for example, in JAX, this primitive language is called LAX. And if you are curious, you can look into the documentation or in the source code, and you will see a huge list of all these primitive operations that are available to you and that know how to differentiate themselves. Okay, one thing I've not really mentioned yet is, and I will ask you at the exam if you have the question, is, okay, in order to run forward or reverse mode autodiff, you need to know the graph of computation in the first place. But where do you get that graph from? So it used to be that you had to write this graph yourself in your code. It's not like this anymore. So this was this ahead of time strategy. Now what we do is that we don't do anything, basically. The library will build that graph for you from the expression that you want to evaluate. So you can just write any Python program, and as the Python code is being evaluated by the interpreter, this graph will be built below for you and stored, such that when you want to differentiate some inputs with respect to some outputs with respect to some inputs, this graph will still be there and will be ready to run, for example, backward or reverse mode autodiff. Okay, and so if you look at PyTorch, that's how it's done. As when you write Python code in PyTorch, the graph does not exist yet. it's only when this code is executed, and as the Python interpreter goes from one instruction to the next, that this graph is built at execution time, okay, and then reused to run the autodiff algorithm. Okay? Okay, another implementation detail is how do we actually compute. So if you remember, for example, for the backward recursive update, we have to compute a sum over all these terms, okay? But usually, especially for us in deep learning, we'll be in a setting where the size of the output, xt, will be 1, typically. Okay, meaning that this first Jacobian is actually not really a Jacobian, it's just a long vector. Okay, which will have to be multiplied with this other Jacobian, which, on the other hand, is a full matrix. Okay? And so what is done usually in efficient implementation is not to have primitives which tell you how to instantiate fully this Jacobian, but instead it's a primitive which knows, given some vector, how to compute this so-called vector Jacobian product. And why is it interesting? Because that's the only thing we care about is the output. We don't care about this intermediate Jacobian, meaning that if we directly target this vector, we can have more efficient, memory efficient, or computation efficient implementations. Okay? So this is what is done technically. It's these vector Jacobian products which are composed to implement backward autodiff. In some libraries, you also have the reverse. So if for some reasons you have actually more outputs than inputs, because you may be doing something else than deep learning, okay, in this case, it might be more efficient to do the forward mode, but in this case, you would need not the same kind of computations. What you would need are Jacobian vector products, okay, which again can be implemented efficiently. And actually, you can go from one to the other, but I will spare you that. Okay, one last thing, or two last things. The first one is checkpointing. So if you run some, let's say, PyTorch code, typically, for example, you would have the architecture of a neural network within a class like this, where you have, in this case, one hidden layer. So you have a linear projection, you have a non-linear activation function, you have the second linear projection, for example, to map vectors of size 100 to vectors of size 10. Let's say if you want to do classification over 10 classes. Then you implement another function which is called the forward, which is how you implement the forward evaluation of your neural network. And typically what you would have is that you have all the intermediate values that you compute in sequence. So you could have x being equal to self layer 1 evaluated at x, then x being equal to self.relu evaluated at x, so the output of the linear, and finally the output computed as the output of layer 2 evaluated at the previous output. And then you return it as the value produced by the MLP. Okay? If you do that, by default, all these intermediate values will be stored in memory. Okay? And that's actually very useful because usually you want to differentiate with respect to all the parameters, so there is a ton to be remembered. And you want these computations not to be repeated. But if for some reason, for example, the size of all these intermediate computations becomes too big, such that you can't store them anymore on your GPU, for example, then, okay, what do? You could say you reduce the dimension of your architecture, but then you will use a lot in capacity. What you could say instead is that actually some of these computations, it would be nice if I could store them, but I'm fine with just throwing them away and recomputing and to recompute them as I need them when I differentiate. And you can do that with what we call checkpointing, where you say, okay, you transform this layer into a checkpointed layer, so that all these intermediate variables are computed as you need them and directly thrown away. Okay, and so that's how you can scale very big neural networks on GPUs. Okay, and finally, I've told you that you can also use this to compute higher order derivatives. So, for example, if you write this Python code in JAX, then you know that as this function will be executed and interpreted, the graph will be computed below. And once you have the graph, you can differentiate. Okay, so that's what this grad function will do. It will produce another function, FP, which will run reverse mode autodiff and so on and so forth. But what you can also do is to call this differentiation function several times, even on itself. How is this possible? If you understand that, you have understood the lecture for today. Yeah.
When it executes each line of the each instruction in the backward pass, it makes a graph, it stores the graph, and then.
Exactly. So we have seen that with backward autodiff, you can differentiate a program. Now, if you want to differentiate this program several times, you need to differentiate the program which differentiates the program. So provided that the program which differentiates is itself differentiable, then as you run it, it will build its own graph of computation, and then you can just run it again on this graph. Okay, and it's exactly how it's done in reality. As you differentiate this graph, the actual graph below will grow bigger and bigger because you will have more. You are differentiating at several order, and so, but it's still a graph, so on top of which you can run this algorithm. Okay. That I will skip, but it was just a demo to show you that indeed this graph is there, grows, and you can differentiate again. What I want to show you instead are a few examples. So for us, automatic differentiation will be useful, of course, to differentiate neural networks and to optimize them. That's like the primary usage, but there are many other applications you could think of. If you are curious, you could look at this video. What they show, and I suppose that's something you have encountered in the past already when you followed machine learning and you had to tune hyperparameters, for example. It was a trial and error, and you evaluate some value, you run your machine learning algorithm for quite a long time usually, then you compute the loss on some validation set, and then you get some number, and then you repeat this whole thing many, many times for different combinations of the hyperparameters. And these parameters could be plenty of things which will control, for example, I don't know, the regularization penalty in a linear model or things like this. Actually, if you see, for example, if you take a linear model with a regularization penalty, let's say, and you want to tune the coefficient that you attach to this penalty, you could do this and naively repeat this whole thing many, many times. Or you could view the training procedure as a program which is differentiable. Okay, so from the inputs to the training up to the evaluation on the validation set, this is just a big sequence of instructions. Okay, which you can express the graph. Okay, and if you have this graph, then you can just differentiate through this entire thing up to the hyperparameter itself. So you could do gradient descent directly on the hyperparameter without doing grid search. That's one use case related to machine learning. There are others, but if you're curious about this one, you can watch this video. The example I will show you is this one. So who knows about fluid dynamics? Okay, good. I don't either. Okay. Do you know how to optimize the wing? The two of you. Okay, I do. Okay, and how can I do that? I can just write a fluid dynamic simulator, and then inside the simulator, I can compute some function that I want to maximize, like the drag lift ratio. And then I will optimize through this entire simulation, provided that the simulator itself is differentiable. Okay? So if you know how to do gradient descent, you know how to optimize the wing. Okay? And I will really show you that. Wait. No. Okay, so let me reconnect to that. Okay, so you could remember your, oh, sorry, your, oh. Ah, désolé, mais ça veut pas du tout aujourd'hui. Okay. All right. So you could remember your class about fluid dynamics and Navier-Stokes, and if you are good enough, you could even understand so well that you can write a simulator to solve these equations. Okay? At the end, it's just a for loop, so it's easy. And so you can do that. You could also put an obstacle in this fluid, okay, and see if this obstacle is lifted upwards or not, okay? And you could describe the geometry of this obstacle as a bunch of hyperparameters, okay? So let's do this. There is a bunch of things to do. But so you would basically implement Navier-Stokes in 2D, for example. Okay, you have your advection, projection, all these things. Then you could use that to simulate a tunnel, a wind tunnel. Okay, and you have all these things, blah, 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 blah. Okay, and then once you have a simulator of wind tunnel, you could define the quality of some geometry for this obstacle, okay, which would happen to be a wing, okay? And so, for example, you could define some function which computes the lift tract ratio, which is some quantity usually that you want to maximize. And the higher the value, the more efficient, in a sense, the wing. Okay? And so this is your objective, which you wrap into this other Python function. Okay? But what you see is that eventually you will call this magic, which is you have this autograd library, which implements this automatic differentiation algorithm, and you will pass directly this objective function, which depends, as you see, on this get lift tract ratio, which itself depends on the entire simulation of the wind tunnel, okay, which itself is this thing which is complicated, which depends on all these other things, okay? Okay, and so, where is it? Okay, then I will call this optimize wing on some values for the shape of the tunnel, the learning rate. I'm doing just gradient descent and other things. This is not really important. Okay, so I'm just showing you there every 2 steps the value of the lift tract ratio. You see that we start from a value of 0.0257 7, and then obviously this value seems to increase. Okay, I did 20 steps of gradient descent on the geometry of this thing. Okay, and this is the result. We start from a rectangle because I don't know anything about aerodynamics, so I just start with this very poor shape of a wing. Then I run the optimization, and the final result looks like this, which looks like a wing. Okay? All of that by just doing gradient descent on a program, which can be arbitrarily complicated, but that's just a detail. As long as this program is completely differentiable, it's made of primitive operations that you can differentiate in isolation, then you can compose this entire program and differentiate through them. Questions? Okay, then that's it for today. Thank you.